All right, so we're going to jump straight into the next chapter. Depending on the edition of the book you have, it's either chapter 22 or chapter 23, I believe. It's all about alpha carbon chemistry. So let's briefly introduce this and kind of define what alpha carbon chemistry is. And we've been spending the last few chapters talking about carbonyl compounds. So a carbonyl compound has the CO double bond in it. And then if we think about the positions, one carbon atom away is called the alpha position. What do you think this carbon is? Beta. So we'll talk about alpha beta chemistry later. We also have gamma over here and delta out here. However, typically we don't do very much with gamma or delta positions until you get into more advanced chemistry. All right, the alpha carbon is unusually reactive. Why? Because of resonance, right? Another way of thinking about this is the pKa of most CHs, meaning most alkanes, is typically around 40 to 50. The pKa of an alpha proton is closer to 20. So we're talking about 20 to 30 orders of magnitude more acidic than a normal alkane because the conjugate base is stabilized via resonance. So now let's take a look at that. So let's take a reaction with a strong base. And we're just going to use generic B as our base. So let's consider acetone. Acetone, we've got 3 alpha protons coming off right here. Does it matter which side we're picking from? No, because they're symmetric. If you're dealing with unsymmetric ketones, you would have to think about it reacting on either side. All right, and if we have a strong base, it's going to grab one of these protons. If it's strong enough, it's really not going to be under equilibrium conditions, so we can show this with a one-way arrow. We can show a negative charge like that, and this negative charge can be pushed all the way up to that oxygen. So this is what we're going to see a lot of in this chapter, is this sort of chemistry where we have some sort of negative charge on that alpha position that we can do chemistry with. This is referred to as an enolate. If you remember, we talked about enols earlier. Enols look a heck of a lot like this, but they have a proton on there. Why do you think we're calling this an enolate? Yeah, anytime you see this ATE suffix, what does that tell you? It's a salt, or it has a negative charge, right? So in this case, we're using a different suffix. We don't call this an enol, we call it an enolate due to that negative charge. The cool thing is you can actually do similar chemistry with catalytic acids. And a lot of this is fairly intuitive, so let's see if we can work our way through this. All right, so if we've got catalytic acid floating around, what do you think the first reaction is going to be? Protonate the oxygen, right? So we're not touching the carbonyl position right away, but that's okay. In fact, sorry, I'm going to change this for Ian. Let's actually show the conjugate base because we do need that. All right, so we can protonate that oxygen. We can think of this being in equilibrium conditions because we know this carbonyl doesn't really like to be protonated. It can be easily deprotonated. And then we also have our conjugate base floating around. We'll call that A-. All right, what do you think could happen next that'll give us a product that looks kind of like an enolate? Yeah, it's going to steal one of the alpha protons because at this point, if we do that, we can kick electrons all the way up to that oxygen and neutralize that positively charged oxygen, right? if you notice, we regenerated our acid over here. So the acid that went in got spit out. That's what makes it catalytic. This, if you remember, is our standard enol, right? So we actually talked about this a fair amount during second term, how to do this transformation. This is called a tautomerization reaction, right? We're just shuttling protons around. Yep.
How in lab practically would you favor, that first equilibrium? Because it's more likely the conjugate base is going to steal that proton back.
So we'll talk about the equilibrium position next. There are various tricks you can do to push the reaction towards the enolate. Favoring the enol isn't always super easy unless you have certain structural features. Yeah. All right, so let's review really quick. We saw this previously with acids. Let's do the same thing with base. I tried to drill this into you second term, so this isn't as jarring. And typically with the base, what do you think the first step's going to be? Yeah, taking a proton, most acidic proton that we have are going to be these alpha protons. So we'll show this with something like hydroxide. All right, just like we saw before, we can kick electrons all the way to that alpha position. And then this negative charge can be delocalized all the way up to that oxygen. Oops. Oops, holy cow, I'm messing up. Here we go. All right, so we've got this resonance stabilized conjugate base. We also have water floating around. Last step, like we saw last term, would just be protonating this oxygen. Why don't we protonate the carbon with the negative charge? Then we're just going backwards, right? That doesn't really show us anything new. So now we can go ahead and we can show our enol this way. And just like we saw with the acid, our base that we put in got kicked out, again making this catalytic. But in either case, we can use this to form an enol. So then the question is, well, why did you show us the enolate? What's the difference? How can we favor the enolate over the enol? So let's take a look at this. Strong base, right? So the enolate is favored when you use a really, really strong base that will drive this out of equilibrium. The bottom ones, if we're looking at it, we're using catalytic acids and bases, meaning we're not using super duper strong bases. Oftentimes we're using more gentle bases. So enolates tend to be favored when you're using a base that's really great. Does that make sense? We'll take a look at the bases that are used to form enolates. Typically, the ones that are favored are things like LDA or sodium hydride. Sodium amide, I suppose you could use. You just don't see it as often in our textbook. Yeah. All right, so now let's think about the equilibrium position for these bottom two. All right. We were kind of being generic in the above examples. Now we'll get a bit more specific. What would this starting molecule be called? Not acetophenone. Cyclohexanone. Yeah. So if we have that, we can treat this with catalytic sodium hydroxide or potassium hydroxide. And what we need to do is think about the equilibrium arrows that would be in the middle box here, but in either case, we could use sodium hydroxide to form our enol and regenerate our hydroxide. All right, so which side of the equilibrium do you think is going to be favored based on everything we've seen so far in organic chemistry? The left side? Yeah, if you remember when we were talking about hydration of alkynes, I said we go to the enol, but the enol quickly tautomerizes to the ketone. That's exactly what we observe here. So the equilibrium, yeah, we might have a little bit of enol in solution, but the reality is it's going to be favoring the ketone side. And we can see this using various forms of spectroscopy that it's about 99.9% on the left-hand side. How do you think we could see this using spectroscopy? Does anybody have an idea? Hydrogen bonding? Sure. Let's think about spectroscopy that we've learned, though. So we've seen IR, so maybe we could see some H bonding, but how could we do it maybe more quantitatively? Proton NMR, right? If we think about proton NMR, in this one we'd see a really unique signal for that proton, right? So we could actually use proton NMR, integrate that peak, and then use that as some sort of internal marker to determine the equilibrium position. It's kind of clever that way. All right, let's take a look at another one. So this one's pretty similar. What is interesting with this one is this will actually favor the opposite direction. So let's try to predict what the enol would look like for this one. In the top one, I gave you the example enol, but this time I want you to determine the enol on your own. So see if you can find the enol. And I guess before we even do that, I'll give you a hint. These methyl groups are alpha positions, right? And they're symmetric, meaning identical. And then this interior group right here is also an alpha carbon. So all of these are alpha positions. Which one do you think is going to be most reactive? The green one? Why? Because of resonance. I'm beating a dead horse here. All right, so let's draw the enol that you would get out. All right, who thinks they got the enol? All right. The tricky thing is we can form the enol on either side. Doesn't really matter, right? All right, so I'll just pick one of these sides. So maybe we put the double bond over there, right? Which means our OH would have to come off this position. And we can't form an enol on the other side without forming some sort of wacky strand system. All right. And then over here, we're also regenerating our hydroxide, which we said in both cases is going to be catalytic. We don't need a full stoichiometric amount. All right, so if you look at the equilibrium arrows, this time I'm telling you the enol is favored over the keto form. Why? Not resonance. Anybody else have an idea? Yeah, so conjugation. So if we think about it, right, this says more conjugation. We know that conjugation provides stability. So if we see we've got alternating double, single, double bonds in this one, that's good. Anything else stand out? The alkene is more stabilized. Yeah, that would be a minor contributor, I would say. Think about that hydrogen off of the alcohol. I can hydrogen bond to that carbonyl, right? So over here, what we have is we have intramolecular H bonding. So in this case, it's unusually stable because when it forms that enol, it immediately kind of bites its own tail and forms this stable six-membered ring. And we can again see this using NMR. And in fact, this one's pretty interesting because this one forms about 70 to 90% of the enol in solution as opposed to the top one where it was like almost undetectable. Does anybody know why the range is so wide? Not quite. Depends on the solvent, right? If you're in an H bonding solvent, you've got competing H bonds with the solvent versus a non-H bonding solvent, you don't run into that competition. So you can actually influence the amount of enol depending on the solvent system that you're using.
So
yep.
I guess then since we see this in NMR, that's sort of the answer to this. We think this happens. So I'm just not why the hydrogen would, why it would bond that side and not the other.
I'm not sure if I understand. Are you asking why is the hydrogen coming off the right oxygen and not the left?
No, it would be nice if you knew what I was asking. That would be
It would be nice if I knew what you're asking. We could talk after class if you want. All right. So now let's think about a even more radical one. All right, this one, we've got hydroxide. Yeah.
So if it's in a H bonding solvent, why is it still favored 70%? Like if it's completely bond.
It's just more favorable to hydrogen bond intramolecularly than to a different molecule. Think about entropy, right? All right, so this next example is even more extreme to the point where it's really not even worth showing an equilibrium arrow. Instead, it'll immediately go and form the enol, which in this case is phenol, plus hydroxide. So essentially, this is 100%. Why? Aromaticity. So really, when I taught you in winter term that the ketone is always favored over the enol, I was lying a little bit. It depends on the situation. However, all the examples we saw in winter term were pretty simple alkanes, right? Which will quickly tautomerize to the ketone. They don't like being in the enol form. However, there are some more exotic examples where you do have to think about conjugation or even aromaticity that may drive it almost exclusively to the enol form. All right, so now let's think about the reactivity here in general terms. All right, so let's think about the reactivity of enols and enolates. We'll start off with an enol. All right, and let's just take a generic enol, a simple one that's easy to draw. In order to look at the reactivity, we first need to look at resonance, right? So let's draw the resonance structure of this. In this case, this oxygen has lone pairs that can be dumped down and form a double bond. And we can kick the electrons from that pi bond over to that oxygen. All right, so if we think about an enol, do you think it's going to be a very good nucleophile or a very good electrophile? It's a little bit weird, but let's think about the carbon, right? So this carbon right here, is that going to be a good nucleophile or electrophile? It's a pretty good nucleophile. So that'll quickly react with any available electrophile. You typically don't see enols acting as great electrophiles because if you were to attack in, let's say right there, you would have a super highly charged intermediate, right? And we would like to avoid that as much as possible. All right, so that's a good nucleophile. Let's think about our enolates. All right, so we did enols first. Our enolates, we said, are the negatively charged cousins. Same idea. We could look at the resonance structures here, which are really, really similar. And again, we could say that this carbon is a good nucleophile. The weird thing with enolates, though, is we have a second nucleophilic position, right? So this is also a good nucleophile. Or let me say decent nucleophile. But not as common. In fact, our textbook doesn't really talk much about reaction at the oxygen position. Instead, we're going to focus primarily on these carbons on that alpha position. They're going to do the bulk of the reactions that we'll see this term. Does that make sense? Yep.
So, in, like, really doing it to get a mixture, but it would mainly be the carbon acting as the nucleophile, or?
As far as we're concerned, we're only going to see the carbon acting as the nucleophile. The reality is it depends on how you form your enolate. So we've kind of been neglecting our countercation at this point, but the cation matters a lot, right? Whether or not it's sodium, potassium, or cesium, the size of that cation will completely change the reactivity of the enolate. That gets into pretty advanced chemistry, so we're going to leave that kind of off our table for the moment. Yeah. All right, so now what we need to do is we need to think about selecting an appropriate base for forming our enolates. So again, we're going to try to get this out of equilibrium and get it exclusively to the enolate. So that's the negatively charged one, kind of like the example up above. All right, so we're going to review a little bit from first term. All right, first term we said we can consider our acid, which in this case we want our alpha protons to be the acidic protons, right? So this is alpha, that means this is our acid. And then we're going to react this with some sort of generic base. And in this case, we want our reaction to go, ideally, as far to completion as possible. Which is going to give our enolate as our conjugate base versus our regular base that we started with. And then over here, we've got our conjugate acid. If you remember, I said there were a few simple things you could do to select an appropriate base, but first thing you need to know is the pKa of your acid. So in that situation where we're dealing with acetone, the pKa of acetone is about 19.2. All right? We said that our acid needs to be stronger than our conjugate acid, right? And I said a good rule of thumb is it should be about 5 pKa units lower than the pKa of our conjugate acid. And then we had our list of potential bases that we could use, but we know immediately off the bat that our conjugate acid should have about what pKa? Like 24, 25-ish. So we can go to that handout that I gave you and try to select a base from there. In general, that rule of 5 works pretty well because that's 5 orders of magnitude difference. That's enough where, for all intents and purposes, it's going one way, right? If you have a difference of 2, yeah, it's still favoring formation of our conjugate base or our enolate, but you're still going to have a considerable amount of your original ketone in solution. All right, so let's take a look at a specific example. All right, in this example, we already said that these alpha protons in the middle are going to be most acidic. And if you actually look this up on a pKa table, it is fairly acidic. It's got a pK of about 9 versus 19 for acetone. So that really shows the resonance stabilization. And in this case, we can go ahead and we can try to predict whether or not this reaction will favor the forward direction, backwards direction, or be in equilibrium. We said that the enolate looks like this, plus water. Okay, so over here, we said we've got our acid, we've got our base. That means that this would be, Oops. Thank you. That should be a negative charge there. So we've got our conjugate acid, or sorry, conjugate base. Whew. And our conjugate acid. All right, so just like we said before, we want to compare our acid to our conjugate acid. Does anybody remember the pKa of water? It's about 15. All right, so are we kind of following that +5 rule? Yeah, definitely. So if we think about this one, this will favor formation of the enolate. Will hydroxide work in the above example, the one we previously did? If we did hydroxide here, we wouldn't really get much of our enolate at all. So we do have to select an appropriate base depending on the pKa of our starting material. So don't forget that material from first term. All right, so let's think about a better base for deprotonating acetone. We need to select a really, really strong base, something that's got a lot more power than hydroxide. So let's go and consider some strong bases. The most common one that you'll see will be this one. That's a good question, but why? So we'll draw out our conjugate acid over here. All right, like we said, the pKa of this is 19.2. The pKa of our conjugate acid is about 36 to 38. So this is a really, really good reaction, right? It's going to favor almost all enolate. Then the question is, well, why go with something so complicated? This looks unnecessarily complicated. Does anybody have an idea why?
It's cheap, it doesn't cost cancer.
I wouldn't say it's even cheap. If we think back to our SN1, SN2, E1, E2 chemistry, we said bases are often also what? Good nucleophiles, right? Is this going to be a good nucleophile? No, it's too sterically bulky to be a good nucleophile, right? So this is chosen because it's so sterically bulky, it's a bad nucleophile. So this works really well for alpha carbon deprotonation because it won't act as a nucleophile not only on the carbonyl itself, but any other functional groups that might otherwise do chemistry. Does that make sense? This is called lithium diisopropyl amide. Yep. And this just gets abbreviated LDA, so you'll probably see me use LDA a fair amount in the book rather than drawing out this complicated molecule. Does that make sense? All right, so now let's look at our first reaction using alpha carbon chemistry. We'll look at alpha halogenation. Oops. All right, so we'll look at this under acidic conditions first. We'll use cyclohexanone. Cool thing with this reaction is you can treat this with catalytic acid and elemental bromine. So typically this is just done mixing bromine and water and adjusting the pH so that it's, slightly below 7. What will happen is you'll get a bromine to install right off of that alpha position. It's kind of nice. So it's just called alpha halogenation because of that. The neat thing with this that becomes more useful later on is we can continue on using this and we can have a base here. And what do you think will happen if we have a base? If we have a base, we can do elimination chemistry and we can get to this special class of compounds called an alpha beta unsaturated ketone. We'll take a look at these later, but they have their own unique reactivity. But this first step over here is kind of what we're going to focus on right now, is how do we get that halogen to install off of that alpha position. All right, so now let's take a look at the mechanism. The mechanism's fairly straightforward and intuitive. If we're treating this with catalytic acid, are we going to get an enolate or an enol? We would get an enol, right? Enolates are only formed with strong bases. We're not dealing with the strong base at all in that first reaction. So now let's focus on the mechanism. We've got our catalytic acid floating around just like we saw before. First step will be to protonate that carbonyl's oxygen. Right, and then once we've done that, we've got these alpha protons hanging out. Water is a decent enough base to grab one of those alpha protons, clamp down, and then kick up electrons to oxygen. But like we said previously, oops, let me include my conjugate acid just for completion's sake. These lone pairs on oxygen can actually delocalize all the way down to the alpha carbon. So that alpha carbon does have an appreciable amount of negative character on it. All right, so we've got all the way to our enol. All right, and then last but not least, whoops, if this reacts with bromine, we know that bromine, we saw this all the way back in January, can be a decent electrophile. So this negative charge can just grab one of these bromine molecules and kick off our other bromide. All right, and then last but not least, we can deprotonate. So I'm just going to write minus H plus to give us our alpha halogenated product. Does that make sense? The main problem I see students make is they don't know which mechanism to use, the acidic mechanism or the basic one. So make sure that you're comfortable doing both mechanisms and try to problem solve your way through it. All right, one tricky thing with this that students will ask about, they'll say, well, can't this continue reacting? Absolutely, it can. So if we push this hard enough, we can actually install multiple bromines on there. However, typically we can control it and stop at one if we want to. All right, so now let's take another example. All right. What happens if we no longer have a symmetric ketone? A black hole forms. Birds fall out of the sky. So if we think about it, I want you to determine, will we get a product that looks like this? Or will we get a product that looks like this? Or will we get a mixture of both? What do you think? Which one would be major, which one would be minor? Or would it be a 50-50 mixture? I don't know what's going on here.
It's like not there, it goes keyboarding.
Whoa. Sorry.
Right there.
Don't use it to look at your laptop, all right?
How would I get this?
All right, does anybody have a pretty strong idea? Few people, what do you think?
What's the one on the right?
The one on the right? Why?
Because there would be more protons for it to attack, so there's better statistic probability.
Okay, so you're arguing that this one would be more favorable due to statistically twice as many alpha protons coming off that position. I think that's a great approach. Does anybody have a different one?
I said the left one because then we have a more substituted alkyl.
Okay, so let's take a look. So let's take a look at the mechanism. I'm going to just do a brief mechanism, not full arrow pushing, but let's think about this, right? We know that our first intermediate, when we have our catalytic acid and water, is going to be the formation of an enol, right? So we could have two different enols form because it's non-symmetric now. We could have this enol on the left and we could have this enol on the right. Which one's more stable? The one on the left, right? It's a more substituted alkene. All right, so now if we think about this, at the next step, we can take a look at this reacting with Br2 and Br2. The reality is we will get a mixture of both of these in solution, but the one that goes through the more stable enol is going to favor the major product. So I would list this as major. And I would list this one as minor. So the statistical probability game, we'll look at that later, that actually does come into play under certain alpha carbon reactions, so you're totally on the right track. But in this case, it's driven by the stability of the enolate. At least that's the theory. Yep.
But wouldn't the bromine be big enough to be sterically hindered by the, in addition to the statistics by the methyl group there?
Yeah, so that's a good point, right? So Ian's point is this carbon right here is acting as the nucleophilic carbon. Wouldn't that, because it's more sterically hindered, have a harder time attacking the bromine? Answer is yes, but in this case, observation says that we're still getting this as our major product. Because bromine is relatively unhindered as an electrophile, it doesn't have a huge impact. Yep. All right. You can also do this under basic conditions. So really quickly before we leave. And this is pretty straightforward, so straightforward, in fact, that we're not going to do the full mechanism. But like we saw previously, we can use catalytic base to get us to our enol. And in this case, we only have one possible enol that can form, right? Because we don't have alpha protons coming off that left-hand side. And then if you react this with Br2, you can again accomplish the same sort of reaction. You just go through slightly different intermediates. So I'm not going to go through the full mechanism, but see if you can get through the full mechanism yourself using the enol formation using catalytic hydroxide. Does that make sense? All right. So I have good news and bad news. Well, I guess good news for most of you. We didn't get as far as I was hoping to in lecture today, so the pod will be an in-class activity tomorrow. Sound good? All right, Thursday. Also, meet with your advisors tomorrow if you need academic advising. If you haven't submitted graduation paperwork, please do so. It's due tomorrow? Yeah, so make sure you get your graduation paperwork in.
I know that somebody, like,
You